Here's a thought. Maybe you've already traveled in time today without even realizing it. Physics shows that the faster you move, the slower time flows for you. That part is real. But the bigger question is, can we actually go back? The answer takes us into wormholes, black holes, and ideas so wild that even Einstein refused to believe them.
In 1940, a telephone conversation took place that can be summarized like this. Hello, I figured out why all electrons are exactly alike. They always have the same charge and the same mass. Why is that? Because they're essentially the same electron, just appearing at different points in space and time. But what about positrons and antiparticles? It's still the same electron, but moving not forward, but backward from the future to the past. From the outside, this would sound like a conversation between two madmen if you didn't know that the first madman was theoretical physicist John Archibald Wheeler, the same one who coined the terms black hole and wormhole, and his interlocutor turned out to be his student, the eminent Richard Feynman, one of the creators of the atomic bomb and, frankly, my favorite physicist. If you're fascinated by the topic, you'll easily notice hundreds, if not thousands, of books, films, and games revolve around the same theme: time travel. I detest most of these stories, and for good reason, but that's not the point today. You've probably heard the common phrase more than once. The laws of physics don't rule out the possibility of time travel. It sounds impressive, but in reality, it means absolutely nothing. Take, for example, the old laws of physics before Newton. They didn't forbid humans from flying either. So what? But we can indeed manipulate time in one sense. This refers to movement into the future. The faster an object moves, the slower time flows for it. This isn't a hypothesis, but a fact, repeatedly verified by experiments. But you must admit, such a trip hardly excites anyone. After all, we're all constantly stepping into the future, accelerating only in our sleep. The real interest is always something else. Is it possible to turn back the clock? Einstein's general theory of relativity predicted many effects that were later confirmed in practice. But there's one astonishing anecdote. In the late 1950s, astronomers discovered objects roughly the size of stars that shone brighter than entire galaxies. These phenomena were called quasars. At first, scientists nearly went crazy. They practically had to invent new physics to explain their nature. But over time, it became clear that there was no miracle involved. Quasars fit perfectly into general relativity. Later, it became clear that they were supermassive black holes that swirl matter around themselves at such a speed that it heats up and emits colossal radiation. Imagine, a theory published in 1915 described a phenomenon that people only discovered half a century later. But the most astonishing thing is that Einstein himself didn't believe in the existence of black holes. He believed that nature would not allow such monstrous objects to form. Meanwhile, a quasar shining 600 trillion times brighter than the sun was recently detected. The scale is so enormous that it's impossible to even imagine. If Einstein with his imagination found it hard to believe, let alone others, it is precisely this ability of a theory to predict the unimaginable, beyond the imagination of even its creator, that makes physics so captivating. Modern science continues this tradition. For example, the detection of gravitational waves by the LIGO-Virgo observatories in 2015, a century after Einstein's prediction, marked a triumph for general relativity and opened a completely new window onto the universe. Or attempts to model the behavior of matter in the extreme conditions of black holes on quantum computers, experiments that just a decade ago would have seemed pure science fiction. Today, there's almost no doubt such terrifyingly powerful objects really do exist, and this is a perfect example of how science doesn't require faith. Your own theories may be smarter than you are. So, no matter how much you doubt the reality of time travel, general relativity still allows for scenarios where it's possible. And what about common sense? It's proven time and again that it simply reflects the prejudices of the era. Let's recall, for example, the scientific community's reaction to Wegener's idea of continental drift in the early 20th century. Common sense seemed to dictate that the continents were immovable. After all, they were so enormous. But geological data, similar coastlines, fossils, didn't fit this picture. Only decades later, with the development of plate tectonics, Did the impossible become a generally accepted scientific reality? Or consider the debate over the nature of light. Is it a wave or a particle? Common sense demanded a choice, but quantum mechanics showed that light is both simultaneously, challenging all conventional wisdom. But when we talk about a time machine, most people conjure up images from movies, some device where you set a date and place and it transports you there. Then comes the discussion of paradoxes. However, this method has much more fundamental obstacles. Imagine we've built a machine, sit down, and decide to travel back in time, for example to 480 BC, to the legendary Battle of Thermopylae. It seems simple, the time is known, the place is known. But the problem is that over the past 2,500 years, the Earth has shifted a colossal distance from its current position, approximately 43 trillion kilometers. If you miss by even a few meters, you could either end up inside a rock or fall from height. And if you miss by millions of kilometers, you're guaranteed to materialize in a vacuum where you'll have to search for the Earth with the telescope. Calculating your exact position is practically impossible.
Another difficulty, the terrain itself is changing. Thermopylae itself has been transformed over the millennia by volcanoes, erosion, and tectonics. And that's not even taking into account buildings, animals, or even air molecules, which could end up inside your body at the point of teleportation, a mortal risk. Even if all this were resolved, inertia remains. The body moves along with the planet and the solar system. If teleported instantly, it would either crash into Earth or fly into space and burn up in the atmosphere. A great analogy would be,
try blindfolding yourself and using tweezers to place an ant on a flying bullet somewhere in the taiga over an area of 100 square miles.
and have it survive. That's the whole simple time machine. Realistic models look different. Several concepts exist, one of which belongs to our compatriot, the eminent astrophysicist Igor Dmitrievich Novikov. He is known for his principle of self-consistency and demonstrated that if wormholes are real, they can be turned into time machines. Many have heard that such tunnels supposedly break causality, but things work differently. Let's say we have a wormhole, one of its throats is near a black hole, and the other is far away. Due to the colossal gravitational field, time passes more slowly near a black hole than farther away. If, for example, a clock lag has accumulated over the years, then a clock near the hole will show an hour behind. And now the main point. Inside the wormhole itself, gravity is minimal and time flows synchronized throughout the entire tunnel. That is, there is no time shift. Imagine that in ordinary space, you can fly from one end to the other in 5 minutes, but inside the wormhole, you can travel in 1 minute. If you start at the upper end at 2 p.m. and fly along the outer path, you'll arrive at the lower end in 5 minutes, where the local clock shows 1:05 p.m. Then you enter the wormhole, spend 1 minute, and return to the upper exit at 1:06 p.m. Congratulations, you've arrived at your starting point 54 minutes early. Sounds great, but a problem immediately arises. Not only humans, but also photons will travel through the tunnel. A single quantum of light will begin to travel back and forth infinitely, creating a massive copies of itself. Their gravity is capable of collapsing the wormhole. Even if you shield it from ordinary light, quantum fluctuations cannot be eliminated. In 1990, Kip Thorne calculated that they would lead to a rapid increase in energy, possibly destructive. Thorne himself believed this was not enough to destroy it. Interestingly, the very nature of these fluctuations is linked to Heisenberg's fundamental uncertainty principle. In the quantum world, a vacuum is not a void, but a seething foam of virtual particles constantly being created and vanished. It is these virtual photons, not actual beams of light, that pose the primary threat to a wormhole time machine. Their energy, though tiny at each point, but infinitely divisible and present everywhere along the path, can accumulate to critical values when attempting to create a closed time-like curve. This makes the problem not simply technical, but deeply physical, linked to the very foundations of quantum field theory. His friend Stephen Hawking believed otherwise and proposed the chronology proof hypothesis. But perhaps the very question of is it possible misses something more fundamental.
The history of science is rife with examples of the impossible becoming reality, but often not in the form originally imagined. Space travel was predicted by Jules Verne and Tsiolkovsky, but real rockets and orbital stations bear little resemblance to their fantasies. Perhaps time travel, if it ever becomes feasible, will turn out not to be a machine in the conventional sense, but something entirely unexpected. For example, the result of manipulating quantum entanglement or properties of the vacuum that we only vaguely understand today. Richard Feynman himself, whose single electron hypothesis is at the origins of this conversation, liked to repeat that nature always turns out to be not only stranger than we assume, but also stranger than we can imagine. And the definitive answer will only come from quantum gravity, when humanity finally understands it.
Thanks for watching. I'd love to see your likes and subscriptions to the channel. Let me know in the comments what you think a real time machine should look like. Check out my other videos in the playlist. Goodbye!